Assalamualaikum and hi, I'm Amira Ikon binti Zaidin, matric number AD190173. I will be presenting about nozzles and diffusers. Nozzles and diffusers are usually used in jet engines, rockets, and even in a spacecraft. Nozzle. Nozzle is a device that increases the velocity of a fluid at the expense of pressure. Diffuser. Diffuser is a device that increases the pressure of a fluid by slowing it down. The cross-sectional area of nozzle decreases in the flow direction for subsonic flows and increases for supersonic flows, while for diffuser, it is opposite. So, the cross-sectional area of diffuser increases in the flow of direction for subsonic flows and decreases for supersonic flows. Nozzles and diffusers are shaped so that they can cause large changes in fluid velocities and thus kinetic energies. Energy balance for this steady flow system can be expressed in the rate form as E in equal to E out m h1 plus v1 squared over 2 is equal to mh2 plus v2 squared over 2. h2 is equal to h1 minus v2 squared minus v1 squared over 2. Common assumptions and idealization are Q equal to 0, which means no time for heat transfer due to high velocity. W equal to 0, nozzles include no shaft or electric resistance wire. And PE equal to 0, which means no change in fluid elevation. Let's try one question for diffuser. Air at 10 degrees Celsius and 80 kilopascal enters the diffuser of a jet engine steadily with a velocity of 200 meters per second. The inlet area of the diffuser is 0.4 meters squared. The air leaves the diffuser with a velocity that is very small compared to the inlet velocity. Determine the mass flow rate of the air and the temperature of the air leaving the diffuser. To determine the mass flow rate, we need to find the specific volume of the air first. This is determined from the ideal gas relation at the inlet condition. V1 is equal to RT1 over P1. We will get 1.015 meter cube per kg. And then mass flow rate is equal to 1 over V1 A1. And then we substitute the values and we will get the final answer 78.8 kg per second. Since the flow is steady, the mass flow rate through the entire diffuser remains constant at this value. Under stated assumptions and observations, energy balance for this steady flow system can be expressed in the rate form as E in equal to E out m h1 plus v1 squared over 2 is equal to mh2 plus v2 squared over 2. h2 is equal to h1 minus v2 squared minus v1 squared over 2. The exit velocity of a diffuser is usually small compared with the inlet velocity, thus the kinetic energy at the exit can be neglected. The enthalpy of air at the diffuser inlet is determined from the air table that we can refer from table A17 to B. H1 is equal to H at 283 Kelvin is equal to 283.14 kJ per kg. When substitute, we will get H2 is equal to the values we substitute, and the final answer we will get is H2 equal to 303.14 kg over kg. From the table 17, the temperature corresponding to this enthalpy value is T2 is equal to 303 Kelvin.
Assalamualaikum. Hi, my name is Nurul Shahadah binti Roslan, metric number AD190198. Today, I would like to present about compressing air by air compressor. So, first of all, what is air compressor? Compressor, as well as pump and fans, are devices used to increase the pressure of fluid. Work is supplied to these devices from an external source through a rotating shaft. Therefore, compressor involve work input. Even though these three devices function similarly, they do differ in the task they perform. Next, a fan increases the pressure of a gas slightly and is mainly used to mobilize the gas. A compressor is capable of compressing the gas to very high pressure. Pumps work very much like compressor except that they handle liquid instead of gases. Heat transfer is negligible for compressor unless there is intentional cooling. Lastly, potential energy changes also negligible for all of these devices. Compressed air is kept under a pressure that is greater than atmospheric pressure. In industry, compressed air is so widely used that it is often regarded as the fourth utility after electricity, natural gas and water. So, next is what is the purpose of compressed air? So, compressed air is used in vehicle propulsion, such as compressed air vehicle, and compressed air also used in energy storage. Next, it is also used in air brakes, which is in railway braking system, in scuba diving for breathing and to inflate buoyancy devices. Then, in gas duster, it is used for cleaning electronic components that cannot be cleaned with water. And the last one is ammunition propulsion. It been used in air gun, airsoft equipment and paintball equipment. For instance, helium is to be compressed from 120 kilopascal and 310 Kelvin to 700 kilopascal and 430 Kelvin. A heat loss of 20 kilojoule per kilogram occurs during the compression process. Neglecting kinetic energy changes, determine the power input required for a mass flow rate of 90 kg per milliliter. So, here is the solution. Helium is compressed steadily by a compressor to a specified temperature and pressure. The power is to be determined. We have three assumptions. First, this is steady flow process since there is no change with time at any point and thus delta MCV equal to 0 and delta ECV is also equal to 0. Second, the kinetic and potential energy are 0, which is delta KE equal to delta PE equal to 0. Lastly, helium is an ideal gas since it is at high temperature and low pressure relative to its critical point value. So, we use energy balance for the compressor, which is E in minus E out equal to dE system over dt. dt is equal to 0 because it is steady flow process. So, E in equal to E out, W in plus MH1 equal to Q out plus MH2. Since we need the value of W in, so we move all of the equation to the right side. So, W in equal to MQ out plus MH2 minus H1 minus MCP T2 minus T1. W in is power, M is mass flow rate, Cp is specific heat of helium at constant pressure, T is temperature. Thus, W in equal to MQ out plus MCP T2 minus T1. M is 90 over 60 kg per second times Q out, which is 20 kJ per kilogram, plus M dot, which is mass flow rate, 90 over 60 kg per second, Cp 5.1926 kJ per kilogram per Kelvin, times T2 minus T1, which is 430 minus 310 Kelvin. So the answer is 965 kilowatt.
Throttling valve are any kind of flow restricting devices that cause significant pressure drop in the fluid. Throttling valves are used to regulate the flow the temperature and the pressure of the surface. This valve can be moved to any position within the stroke of the valve and hold that position, including full open and also full closed position. The pressure drop in the fluid is often accompanied by a large drop in temperature, and for that reason, throttling devices are commonly used in refrigeration and air conditioning applications. A throttling process is a process which there is no change in enthalpy from one state to another state, which is H1 equal to H2.
So for this question, this is the illustration shows, and this is the inlet and this one is the exit. So the pressure that enter this throttle is at 700 kPa and leave at 160 kPa. So for this question, it asks what is the temperature drop and also the specific volume at the exit of the throttle. So we're gonna use the first law of thermodynamics, which is this equation: Q minus with W equal to difference of enthalpy plus with kinetic energy and plus with potential energy. For this question, we assume that it's negligible, so the energy is 0. W is 0. Kinetic energy is 0, and also potential energy is 0. So you're gonna get this one, H1 equal to H2. Okay, next at P1, which is 700 kPa, we need to refer to table A12, and then from the table we need to find the 700 kPa, and then we will find the value of H1 equal same with HF equal to 88.82 kJ per kg, and also T1, which is T saturated, equal to 26.69 degrees Celsius. And then for P2, which is 160 kPa, we will refer to table A11. This is because we need to find H2, which is between HF and also HFG. And then from the table, we will find the HF value, which is 31.18 kJ per kg, and then HFG, which is 209.96 kJ per kg. And then we need also to find the specific volume for VF and also VG, and this is the value for each respectively. And also we need to find the temperature, which is negative 15.6 degrees Celsius from the table. Now, after we get all the information regarding this question, so we can go through the first question, which is find the temperature drop of the refrigerant. We're gonna use the value of T1 minus with T2, this one, and then we will get the final answer for temperature drop, which is 42.26 degrees Celsius. Next question is to find the specific volume at the exit of the throttle, which is V2. So we're gonna use this equation, enthalpy equal to HF plus X2 quality 2 times with HFG. So we include all the value, and then we're gonna find the X2 0.2745, and then we use this equation, specific volume V2 equal to VF plus quality 2 times with VG minus VF. Enter all the value, and then we're gonna get the answer of specific volume, which is 0.0345 meter cube per kg. That's all for throttling valve. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Haikal Hakimi bin Ahmad. My metric number AD190192. So for today, I will present about heat exchanger. So what's the meaning by heat exchanger? Heat exchanger are two devices where two moving fluid streams exchange heat without mixing. Heat exchangers are widely used in various industries and they come in various designs. So for common assumption for heat exchangers, W0 equal to 0, delta PE equal to delta KE equal to 0. Q0 could be different depending on the selected constant variable. See the next example. The mass and energy balance become M1 equal to M2 and M3 equal to M4. And the other equation is M1 H1 plus M3 H3 equal to M1 H2 plus M1 H4. So these are some applications of heat exchanger that had been used in industry. We go for the question. Engine oil is to be cooled by water in a condenser. The engine oil enters the condenser with a mass flow rate of 6 kg per minute at 1 megapascal and 70 degrees and leaves at 35 degrees. The cooling water enters at 300 kilopascal and 15 degrees and leaves at 25 degrees. Neglecting any pressure drops, determine the mass flow rate of the cooling water required. So, if you look at here, the equation give m.1 equal to m.2 equal to m.water, and the second equation m.3 equal to m.4 equal to m.oil. So the conservation of energy equation is q dot minus w dot equal to summation of m.e, open the bracket, and then he plus v is squared over 2 plus gze, and then close the bracket, minus summation of m.1, open the bracket again, and then h1 plus v1 squared over 2 plus gz1, and then close the bracket. Next, summation of m.e multiple with he equal to summation of m.e multiple with he. Next, m.water multiple with h1 plus m.oil plus m.oil again, and then multiple with h3 equal to m.water multiple with h2 plus m.oil multiple with h4. So last, m.w equal to h3 minus h4 over h2 minus h1 multiple with m.oil. So next, we assume that constant specific heat for both the oil and water at their average temperature. So m.w equal Cp oil, open the bracket, T3 minus T4, close the bracket, over Cp water, open the bracket, T2 minus T1, close the bracket, and then multiple with m.oil. So we insert the value 2.016 kilojoule over kilogram dot C, close the bracket, and then we multiple with the value of T3 and T4. So 70 minus 35, so over 4.18 kilojoule over kilogram dot C. So we multiple with the value of T2 minus T1. So here we get 25 minus 15. So we multiple all the value, we multiple with value of m.oil. So we get 6 kilogram per minute. So the last answer, the final answer, we get 10.1 kilogram per minute. That's all for me. Thank you.
So what is pipe and duct flow? Flow through a pipe or a duct usually satisfies the steady flow conditions and thus can be analyzed as a steady flow process as it excludes the transient startup and shutdown periods. It is used to transfer liquid from one device to another. For example, in this case, are the water flow through the pipes in the furnace of a power plant, the flow of refrigerant in a freezer, and the flow in heat exchangers. The velocities involved in pipe and duct flow are relatively low, and the kinetic energy changes are usually insignificant. This is particularly true when the pipe or duct diameter is constant and the heating effects are negligible. Kinetic energy changes may be significant, however, for gas flow in ducts with variable cross-sectional areas, especially when the compressibility effects are significant. The potential energy term may also be seen when the fluid undergoes a considerable elevation change as it flows in a pipe or duct. Now we will try to answer a question to test our understanding. So the question is, the electric heating systems used in many houses consist of a simple duct with resistant heaters. Air is heated as it flows over resistant wires. Consider a 15 kilowatt electric heating system. Air enters the heating section at 100 kilopascal and 17 Celsius with a volume flow rate of 150 meter cube per minute. If heat is lost from the air in the duct to the surroundings at a rate of 200 watt, determine the exit temperature. Hence, three assumptions can be made, which is number one, this is a steady flow process since there is no change with time and any point, and thus delta MCV is equivalent to 0 and delta ECV is equivalent to 0. Number two, air is an ideal gas since it is at a high temperature and low pressure relative to its critical point values. Last but not least, the kinetic and potential energy changes are negligible. For the solution, we take the heating section portion of the duct in the system as shown in the figure. This is a control volume since mass crosses the system boundary during the process. We observe that there is only one inlet and one exit, and thus m.1 equals to m.2 equals to m. Also, heat is lost from the system and electrical work is applied to the system. For temperatures encountered in heating and air conditioning applications, delta H can be replaced by Cp delta T, where Cp is equivalent to 1.005 kJ per kilogram Celsius. Then, the energy balance for this steady flow system can be expressed in the rate form as rate of energy transfer by heat, work, and mass is equivalent to the rate of change in internal kinetic potential energies is equivalent to 0. So from here, we have E dot in equals to E dot out. Hence, we can derive it as W dot E in plus M dot H1 is equivalent to Q dot out plus M dot H2, where we will get W dot E in minus Q dot out is equivalent to M dot Cp delta T. Now, we need to find the specific volume of air at the inlet of the duct by using the ideal gas relation, which is V1 equals to RT1 over P1, where T1 is equivalent to 17 Celsius, where we need to convert it to Kelvin. Hence, we need to add 273 Kelvin equals to 290 Kelvin. For P1, we have it as 100 kilopascal. And the R value is 0.287 kilopascal meter cube per kilogram Kelvin. Substitute the values. Hence, we will obtain an answer of 0.832 meter cube per kilogram for the specific volume.
For the next step, we need to find the mass flow rate of the air through the duct by using the formula of m dot equals to v dot 1 over v1, where v dot 1, also known as the volume flow rate, is equivalent to 150 meter cube per minute, whereas the v1, or also known as the specific volume of air in the inlet duct, is equivalent to 0.832 meter cube per kilogram. Now we need to substitute the values in the formula. And we also need to convert this into seconds. So now we will obtain an answer of 3 kilogram per second. From the question, we need to find the exit temperature, or also known as T2. We have also calculated certain values such as the rate of mass transfer, which is 3 kilograms per second, Cp 1.005 kilojoule per kilogram Celsius, T1 equals to 17 Celsius, W dot En equivalent to 15 kilowatt, and we have converted it into 15 kilojoules per second. Q dot out is equivalent to 200 watts, and we have also converted it into 0.2 kilojoules per second. So now we need to use the formula that we have derived earlier, which is W dot En minus Q dot out is equivalent to M dot Cp delta T. Now we need to substitute the values. By calculating it and solving it, we will get the value of T2 as 21.9 Celsius.